Hi, welcome back to Ask a Creationist. I'm Todd Wood. I'm president of Core Academy of Science, and I'm a young age creationist. I'm here to answer your questions about creation, evolution, origins, science, faith, the Bible, Genesis, whatever you got. We're interested in hearing from you. Maybe we'll feature one of your questions on a future episode of Ask a Creationist. Let's get to this week's question. So this week we are continuing our journey through the evidence against evolution, or perhaps more properly, we might think of it as evidence that is inconsistent with or poorly explained by evolution. Now, last time, we considered the case of geographical distribution on oceanic islands, and I said that the evidence for evolution there is really interesting. It makes sense to me that unique species on oceanic islands would be derived from the nearest mainland. It makes sense to me that they would be closely similar to the species on the nearest mainland. But in fact, you don't get very far with that. In terms of inferring macroevolution, you only get unique genera, unique species, nothing really shockingly different. But I also said that we would have to consider the question of continental islands, which are quite different from oceanic islands, in the sense that continental islands are, well, parts of continents. And looking at the species diversity and divergence here, we're going to sort of have to make some inferences. So one of them might be that longer isolation might equal greater endemism. So the longer two pieces of land have been separated and evolving separately, the more likely it is that on the island you will find things that are really very different from the things that you might find on the mainland. The age of the island, the distance from the mainland, the ocean currents, the direction that the ocean currents travel, they will all contribute to this question of isolation. So this isn't going to be a real simple thing to interpret, because there's going to be lots and lots of different complicating factors that we're going to have to be reasonable and fair about, and not say evolution can't explain this, because that's not going to be exactly correct here. And of course, we also have to keep in mind that geographic area contributes to a number of species. The larger the landmass, the more possibility of unique species thriving and finding their own special areas to live. All right, so what are we going to talk about in terms of continental islands? Well, I want to talk about Madagascar. This is an island that has complex origin. In the conventional model, it's separated from Africa about 160 million years ago, and then around 90 million years ago separated from India. India kept cruising up the Indian Ocean to crash into Asia to produce the Himalayas, and Madagascar basically stayed behind as an island near the southern end of Africa. It's about 229,000 square miles, which is about 40% bigger than California, and it's about 250 miles from the African mainland at its nearest point. And not surprisingly, about 80 to 90% of the taxa that you find there, the animals and the plants and so forth, are endemic. They are found only in Madagascar. And the most important thing from our perspective is that there are whole families found only here. And this is something that we definitely noticed was different from oceanic islands, or from most oceanic islands, I should say. The degree of divergence, the amount of difference, is much bigger here on Madagascar than you would find on an average oceanic island. And there are many famous examples that we can give, including the lemurs, number of flowering plant families, and elephant birds. The largest flightless bird was found on Madagascar. It is now, unfortunately, extinct, but it once was part of the Madagascar animals and creatures. So let's have a look first at these unique flowers. This particular flower here represents a family called Sarcolinaceae, and there's about 70 species of Sarcolinaceae found only in Madagascar. So the pink color here represents the distribution of Sarcolinaceae found only there in Madagascar. Now, if Sarcolinaceae colonized Madagascar from the nearest mainland, then we would expect that it would be very similar to something on the nearest mainland, right? And sure enough, we find that the most similar thing to Sarcolinaceae is a family called Dipterocarpaceae, which is found in Africa, southern Africa, and in Southeast Asia. So this makes a lot of sense from sort of an evolutionary perspective. Sarcolemmaceae as a unique family is derived from perhaps some common ancestor with Dipterocarpaceae, at least from the evolutionary perspective. It isn't always that simple, though. So another example might be those lemurs, right? We're all familiar with lemurs. Turns out there's 3 of these primate families that contain the lemur species. There are over 100 species of lemurs. You might not have known that. You might be familiar with the ringtail, but you might not know that there are a lot of other lemurs as well. Now, let's think about this carefully. The evolutionary story tells us that primate, and in fact placental mammal diversification, began in the Cenozoic. Once the dinosaurs went extinct, then the different mammal groups began to really take hold and diversify and produce unique forms that basically replaced the niches that were left behind by the dinosaurs. But Madagascar broke away from Africa in the Jurassic, which is millions of years earlier on the conventional timescale. So in fact, the lemurs are not simply something that would have been part of that break apart. They must have come in later. So the ancestors of the lemurs must have rafted to the island, like an oceanic island, and then left descendants only there, but not on mainland Africa, which is a really peculiar thought. So we have these lemurs. There are no lemurs in mainland Africa, and they left only descendants there in Madagascar, thus making the Madagascar lemurs unique and endemic and not found in Africa. And this story would be true for any indigenous mammals. They all would have to be creatures that rafted to the islands after the breakup of Africa, India, and Madagascar. So this throws a little wrinkle into things. We said that it makes sense that highly divergent things would be something that would have been there very early and isolated for a very long time. And here we find that, in fact, probably they rafted there. So the story is more complicated. Another big story for the southern hemisphere are the ratites. Series of flightless birds shown here in a rough approximation of their height. And you can see you've got your kiwi bird from New Zealand, you've got your emus from Australia, rheas from South America, ostriches, very familiar, from Africa, and then, of course, the elephant bird endemic to Madagascar. As I said, these are all southern hemisphere birds. So if this is a story of, say, the southern continent breaking up and these birds all diverging from that, such that there used to be one population of these sort of flightless ratites that occupied a piece of the southern continent that eventually broke apart into Australia, Africa, South America, and Antarctica, then we would expect that the geographic proximity should approximate the evolutionary divergence. So we would expect that ostriches would be very closely related to the elephant birds. And that makes a lot of sense because ostriches and elephant birds are the largest of all these birds. We would also expect the emus from Australia and the kiwi bird from New Zealand also to be closely related because they're geographically close together. And that turns out to be wrong. So very recent phylogeny of the ratites, including the elephant bird here. This is from DNA sequences. And you can see what I just told you is incorrect. So if we map these out to where they occur, we find that this is just really bizarre. So the ostrich from Africa is the most evolutionarily primitive of these ratite birds. The elephant bird is most similar to the kiwi. So what that means is, and the authors of this particular phylogeny basically said that there must have been flying ratites. The other thing that brings this out is the tinamous. Tinamous are South and Central American species. They're not flightless. They can fly. They don't fly very well, but they can fly. And they're closely related to the moas, which is a series of ratites, flightless ratites that are found only on New Zealand. The authors of this phylogeny argued that we must be seeing the origin of this flightless form, the basic ostrich-looking form that we find in rheas and emus and kiwis and so forth, elephant birds. It must have originated multiple times. And that most of the ancestors here probably had some capacity for flying. Otherwise, how do you explain kiwis on one side of the world being closely related to elephants on the other side of the world? I don't know. It's pretty peculiar. So does this mean this is, evolution is a failure and can't explain the biogeography of Madagascar? I don't think so. I think what this means is that stories of these origins of these species are just more complicated than we like to think. We see things, we see the ratites only found in the southern hemisphere, we see the elephant bird and the ostrich right next to each other, and we think, well, that makes sense then. The southern continent broke up, these things diverged, and you have the largest species right next to each other. And that turns out to be wrong, right? That story turns out to be wrong. It's just more complicated. Same for the lemurs. It's not that the deep, deep ancestors of lemurs were there when Madagascar and India and Africa all broke up geographically. It's that they rafted in. And one could argue that there are reasons for modeling and so forth to support this. So it's not that Madagascar reveals the failure of evolution. It's that Madagascar reminds us that things are more complicated than we think. So thanks for watching this episode of Ask a Creationist. If you enjoyed that, please leave a like. And if you really enjoyed it, subscribe and click the bell to receive notifications when we put up a new video. Also visit us online at coursei.org. There you'll find ways to interact with us and submit questions for Ask a Creationist, future episodes. You'll also find us on Instagram, Twitter, and Facebook. You can interact with us there. If you disliked this video, leave a dislike. The more interaction we get on our videos, the more people will watch them. So thanks for watching. Thanks for participating. See you next time.